Hello students, welcome to Learn It. So in conclusion, we can see a standard electrode potential which is represented by the symbol E0, which is always calculated at NTP. So with respect to hydrogen, E0, that is hydrogen, is converted into cation. It means oxidation potential, that is standard oxidation potential of hydrogen electrode is 0 volt. Similarly, E0, that is cation to molecule, it means reduction. So standard reduction potential of hydrogen electrode is 0 volt, because we already know that at NTP in the hydrogen electrode there will be no oxidation and no reduction. So standard electrode potential E0 with respect to zinc we have already discussed. So E0 of zinc, that is Zn, is converted into Zn plus 2, it means oxidation. So standard oxidation potential of zinc is 0.76 volt. Similarly, with respect to lithium, standard oxidation potential of lithium is 3.05 volt. So by this we can conclude that lithium has more standard oxidation potential than zinc. Similarly, we need to discuss about the electrodes which undergo reduction at NTP. It means the electrodes which are cathode at NTP. So we know two examples. First one is copper, second one is silver. So the question comes, between copper and silver, which electrode has more tendency to accept the electron, or which has more reduction potential? And the second question is how to measure it. So as before, we measure it by using standard hydrogen electrode. So we take the copper electrode and connect it with the standard hydrogen electrode. So here the platinum wire of standard hydrogen electrode is connected to copper by external wire. In between them the voltmeter is placed. Circuit is not complete because these solutions are not in contact, so that's why we use the salt bridge. At this time the voltmeter shows the reading of 0.34 volt. Here the hydrogen is undergoing oxidation because the copper is undergoing reduction. So standard oxidation potential of hydrogen is 0 volt. So it means that this 0.34 volt is the standard reduction potential of copper electrode. This cell is represented by the symbol platinum, that is this platinum wire. It is in contact with the hydrogen, which is the gaseous state, which is in contact with the H plus ions whose concentration is 1 molar, which is connected to salt bridge, so which is represented by double bar, which is in contact with copper plus 2 ions whose concentration is 1 mole, which is in contact with copper, which is solid. So here left hand side is anode, so hydrogen acts as an anode which is in contact with the cathode, that is copper electrode, through salt bridge. If we take the hypothetical cell in which anode is hydrogen, cathode is copper, so if we connect the voltmeter, then it shows the reading of 0.34 volt. So the same cell is represented here. So at the anode there is an oxidation, so hydrogen is converted into H plus ions. It means that hydrogen gas converted into H plus ions. So the concentration of H plus ions increases. There will be increase in H plus ion concentration. So at the cathode, the copper will be deposited. It means that Cu plus 2 ions starts to deposit. You can see here. So the overall reaction is the hydrogen, that is hydrogen gas, is converted into H plus. So it means that it is giving the electrons. So these electrons come and sit here, and so these electrons are taken by Cu plus 2 ions. So as we discussed before, what if we take copper and we put it into acid? So this is an acid. H plus ions means acid. So when we put copper, there will be no reaction, because we know that copper wants to undergo reduction, not the oxidation. So that's why this reaction doesn't happen. Similarly, when we take hydrogen electrode and connect it with the silver electrode, here we are going to connect hydrogen, that is platinum wire, with the silver. In between them, voltmeter is placed, and the solutions are not in contact, so we introduce the salt bridge. So this time the voltmeter shows the reading of 0.80 volt. This 0.80 volt is the standard reduction potential of silver electrode. This cell is represented by platinum, which is in contact with hydrogen, which is in contact with H plus, which are connected to salt bridge, which are in contact with silver ions whose concentration is 1 mole, then silver, which is solid. So here hydrogen acts as an anode, silver acts as a cathode. So if we take hypothetical cell, so this is already a cell, but we are taking it as an example. So if we take a cell in which one part, that is anode, is made up of hydrogen electrode, cathode is made up of silver electrode. If we connect the terminals of this cell to voltmeter, then voltmeter shows the reading of 0.80 volt. So here anodic reaction is again the same, that is decomposition of hydrogen into H plus ions. In the cathode, silver is deposited. So this is the overall redox reaction. So if we take the acid and if we put the silver, then there will be no reaction, because silver wants to gain the electron and H plus, that is hydrogen, wants to undergo oxidation, but here no hydrogen, H2 is not there, and here no Ag plus. So that's why there is no reactant side, only products are there. So backward reaction is not possible. In conclusion, if we look at the standard electrode potential E naught for copper, represented as Cu plus 2 is converting into Cu. It means that cation is converting into atom. So this shows standard reduction potential. So standard reduction potential of copper is 0.34 volt. Similarly, if we look at the standard reduction potential of silver electrode, then it is 0.80 volt. It means the standard reduction potential of silver is more than the standard reduction potential of copper electrode. It means the silver wants to undergo reduction more than the copper. So until now we discussed about the two types of standard electrode potential. The first one is standard oxidation potential. The second one is standard reduction potential. So let us arrange them. So here hydrogen is at the middle. because it is having the standard reduction potential or standard oxidation potential whose value is 0. Copper, whose standard reduction potential value is 0.34 volt. So it is above the hydrogen, but it is below the silver because it is having the value 0.80 volt. The zinc is having the standard oxidation potential value, that is 0.76 volt, but it is below the lithium. So if we add some more elements like fluorine, because we know fluorine is the most electronegative element, then it will occupy the position first in the standard reduction potential value. And the lead, it comes between hydrogen and zinc, whose value is 0.13. It is standard oxidation potential. So here, if we analyze, the lithium is having the highest standard oxidation potential value. So this is one of the reason why lithium batteries are efficient energy storage devices. So as to curb the confusion of standard reduction potential and standard oxidation potential, we come across the consideration that convert all the oxidation potential value into negative of reduction potential. It means that lead, which is having the 0.13 oxidation potential value, converted into negative of 0.13 volt. It is understood that negative values indicate the standard oxidation potential. So we get a list. Here the elements are arranged in the increasing or decreasing order of their standard reduction potentials. Then this arrangement is called as electrochemical series. Here we have the bigger electrochemical series. As the space was not available, I put into 2 slides. So we can see hydrogen is at the bottom. It means that all the elements above it are having the positive standard reduction potential. Fluorine is at the top. Here it indicates the reaction. Here it is the standard reduction potential value. And this list is in the decreasing value of standard reduction potential. So here the hydrogen is at the top, means that all these elements are having the negative value of standard reduction potential. You can see lithium is at the bottom, whose reaction is this, and the standard reduction potential value is minus 3.05 volt.